Hello and welcome to the lecture on 10.5. Today we're going to talk about inverses of matrices. First thing I want to do is recall what an inverse and an identity are. Recall AX equals B. This is just a system of equations. Now, we'll talk about this a little bit more later, but for right now, I just want you to remember what this is and how we can solve this. If I could get rid of this A, then I would have X is equal to something. That's the point here. So remember that an identity does not change the value under an operation. So we would have different identities depending on which operation we're using. For instance, we've talked about this in chapter 1. 1 times A is equal to A. This means that 1 is the multiplicative identity, because it doesn't change anything. When you multiply by 1, the value is unchanged. Similarly, 0 is the additive identity. Again, because if we add 0 to anything, then nothing changes. The inverse of an element A for an operation is the element that changes A to the identity under that specific operation. So we know that 1 is the multiplicative identity and 0 is the additive identity. So if I have a value A, what do I need to multiply by A to get 1? So whatever this is, whatever goes here in this blank, this is going to be the inverse of A under multiplication. And it is 1 over A. When we multiply 1 over A times A, we get to the multiplicative identity. And similarly, with the additive inverse, we want to get A to be 0. So what do I need to add to A in order to change A to 0 under the operation of addition? That's going to be negative A. Negative A is the additive inverse of A because it changes A to be the additive identity. Now we're going to do something similar here with matrices. Now remember, matrix multiplication is different than regular multiplication. So this is a little bit more challenging because our elements are going to be matrices instead of these values A. Let's ask ourselves, what is the identity matrix? Because here, in order to have an inverse, we need an identity. Because we can't get to an identity if we don't have one. We can't change our A to an identity if we don't know what that identity is. So we need to figure out what the identity matrix is first, and then we'll get to the inverse under matrix multiplication. A square matrix is a matrix with the same number of rows and columns. Now, this should be relatively intuitive. We'd have a certain number of rows and a certain number of colors that's equal, and that will generate what we call a square matrix because it looks like a square. The main diagonal of a square matrix consists of the elements A11, A22, all the way up to A sub n. Now, this is just the elements from the top left corner of a square matrix to the bottom right corner of a square matrix in a straight line. So for instance, if we had a matrix 1, 2, 3, 4, our main diagonal consists of 1 and 4. This would be A11, this would be A22. And we could get even larger, and we would have this as our main diagonal. 1, 6, 11, 16. A11, A22, A33, A44. Before we can even talk about inverses, we need to know what the identity matrix is. The identity matrix, denoted I sub n, is the n by n matrix for which each main diagonal entry is 1 and all other entries are 0. So it'll look something like this, where we have I sub 2, this would be the 2 by 2 matrix, 1, 0, 0, 1. I sub 3, this would be the 3 by 3 identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. And we'll go up to the 4 by 4 identity matrix. And that is going to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So on the main diagonal, we have ones. Everywhere else, we have zeros. These are the identity matrices. Now remember what an identity is. It doesn't change an element under a specific operation. So we have an identity does not change the value under an operation. When we talk about the identity matrix here, we're talking about matrix multiplication. So these matrices are the matrix multiplicative identities. Show you. Suppose that we have A is equal to 1, 2, 3, 4. And I'm going to multiply it by I sub 2, which is 1, 0, 0, 1. Now, it obviously would not make sense to multiply I3 by this matrix because it's a 2 by 2 matrix. And that's impossible to multiply a 3 by 3 by a 2 by 2 matrix. So A times I will be 1, 2, 3, 4 times 1, 0, 0, 1. And remember how we do our matrix multiplication. We multiply this row by this column. So it'll be 1 times 1 plus 2 times 0. And that will be the 1, 1 entry. So 1 times 1 is 1, 2 times 0 is 0, 1 plus 0 is 1. And then we move on to the next column. 1 times 0 plus 2 times 1. 1 times 0 is 0, plus 2 times 1 is 2. So we get a 2 here in the first row, second column. Now second row, first column, that would be this entry. 3 times 1 plus 4 times 0. So 3 plus 0, 3. And then second row, second column, which is here, the second row, second column entry. 3 times 0 plus 4 times 1. 3 times 0 is 0, 4 times 1 is 4, so we have 0 plus 4 is 4. Now notice it didn't change A at all. 1, 2, 3, 4, 1, 2, 3, 4. That's what an identity is supposed to do. Now we could also do I times A and we would get the same thing. 1, 0, 0, 1. I just want to show you this because we know that not all matrix multiplications are commutative. With the identity, it should always be commutative because the identity doesn't change the matrix at all. 1 times 1 is 1, plus 0 times 3. This would be the first row, first column. So our first row, first column entry will be 1 times 1 plus 0 times 3. It's 1 plus 0. First row, second column, 1 times 2 is 2, plus 0 times 4. So we have 2 plus 0. It would be this first row, second column. And then second row, first column will be this entry here at the second row, first column. 0 times 1 plus 1 times 3. And then second row, second column, second row, second column. 0 times 2 is 0 plus 1 times 4. Do need to make a note here that only square matrices have an inverse, which is what we're going to talk about next. What I want to talk about next is the inverse of a matrix. Let A be an n by n matrix. If there exists a matrix A to the negative 1 power with the property that A times A to the negative 1 equals A to the negative 1 times A equals I sub n, then we say A to the negative 1 is the inverse of A. Now, generally, we're not going to say A to the negative 1 power. It's not exactly correct to state it that way. We call this A inverse. Now, the reason I didn't want to call it A inverse here was because we're defining it here, and calling it the inverse of A doesn't make sense when we are trying to define something. But A times A inverse will equal I, and A inverse times A equals I. Now, I do need to note a couple of things. One, remember what an inverse is. This fits with the definition of what an inverse is according to an element and an operation. Remember, an inverse requires an element and an operation. So 1 over A is the inverse of A under the operation multiplication. Negative A is the inverse of A under the operation of addition. Here we have A inverse is the inverse of A under the operation of matrix multiplication. That's one thing that I wanted to note. The second thing I'm actually going to write out because it's important. Note, only square matrices have an inverse. A is an n by n matrix. So right there, we immediately say that it's going to be, that A has to be an n by n matrix. I is going to be the result of the product of A and A inverse. Furthermore, A times A inverse is equal to A inverse times A. So A inverse and A are commutative. So this might be obvious to you because A times A inverse and A inverse times A are both defined, and they're defined as I sub n. Right, so if let's say that A is m by n, right, then A inverse would have to be n by m. But this would give us I sub m, which would be the inverse with m rows and m columns. And if we commute these two, and we have A inverse, which would be an n by m, times A, which is an m by n, we would get I sub n, which is different number of rows and columns. The only way that these two are the same is if m is equal to n, which gives us a square matrix. So A needs to have a square matrix, which means the only matrices that have an inverse are square matrices. Now let's show you what this actually looks like. Let's say that our A is equal to 1, 1, 3, 4. Now I'm going to give you A inverse because I want to multiply these two together to show you what happens here. 4, negative 1, negative 3, 1. So A times A inverse will equal 1, 1, 3, 4 times 4, negative 1, negative 3, 1. If we do this product, we have 1 times 4 plus 1 times negative 3. So 1 times 4 is 4, 1 times negative 3 is negative 3, 4 plus negative 3 is 1. We get a 1 here. First row, second column, 1 times negative 1 is negative 1, 1 times 1 is 1, and when we add them, we get 0. First row, second column. Now we're doing the second row, first column, so the second row, first column entry. 3 times 4 is 12, 4 times negative 3 is negative 12, and when we add those two, we get 0. Then the second row, second column, so we do the second row, second column entry. 3 times negative 1 is negative 3, 4 times 1 is 4, so negative 3 plus 4 is 1. So we have our identity. I'm going to do the next one very quickly. A inverse times A, and we have 4, negative 1, negative 3, 1 times 1, 1, 3, 4. This is my A. This is my A inverse. 4 times 1 is 4. Negative 1 times 3 is negative 3. 4 plus negative 3 is 1. 4 times 1 is 4. Negative 1 times 4 is negative 4. When we add those, we get 0. Negative 3 times 1 is negative 3. 1 times 3 is positive 3. When we add those two, we get 0. Negative 3 times 1 is negative 3, plus 4 times 1, which is 4. We get a 1 here. So the inverse actually does not matter which order you multiply it to the actual matrix A. If it is the inverse, it will give you the identity in either order. All right, the next topic I want to cover is going to be finding the inverse of a 2 by 2 matrix. Inverse of a 2 by 2 matrix. If A equals A, B, C, D, then A inverse is equal to 1 divided by AD minus BC times the matrix D, negative B, negative C, A. If AD minus BC equals 0, then A has no inverse. And we can see that here because you would be dividing by 0. Now what you do to find the inverse is you do 1 divided by AD minus BC, so the AD minus B times C. And you swap the positions of A and D. Notice here we had an A in the top left in the position first row, first column. Now our A is second row, second column. D was in the second row, second column. Now it's in the first row, first column. And we negate first row, second column, and second row, first column elements. So B is now negated, and C is now negated. Now, we haven't talked about this yet, but we will talk about this soon. This AD minus BC has a specific name. It's called the determinant. And having this determinant equaling 0 means that A has no inverse will be a recurring theme. I'm going to prove this to you really quickly here. So let's say that we have the matrix A, B, C, D. I want to multiply by this matrix to show you that this matrix is in fact the inverse of A. So let's do A inverse times A. I'm not going to do the other way. I'm just going to show you this one way. So we have 1 divided by AD minus BC, B, negative CA, and we're multiplying by A, which is A, B, C, D, where A, B, C, and D are just numbers. Now, D time, when we do this multiplication, remember it's in the first element in the first row, first column. I'm going to leave this out. And then for our matrix, first row, first column will be the first row of A inverse times the first column of A. B times A plus negative B times C. So we get AD minus BC. In the first row, second column, that would be the first row of A inverse times the second column of A. You have D times B plus negative B times D, which is just 0. Basically, BD times BD plus a negative BD. Second row, first column, negative C times A, negative AC, plus A times C. So negative AC plus AC is 0. And then second row, second column, be the second row times the second column here. Negative C times B is negative BC plus A times D. So again, we get AD minus BC. As you can see, when we multiply this in, it will cancel out with my AD minus BC here, and we'll just be left with 1s in those locations. So we get the identity, the 2x2 identity. Do the example. Let A equal 1, 4, 2, 3. Find A inverse. Well, A inverse is just going to be A times D minus B times C. So 1 times 3 minus 2 times 4. Under 1. And then we change the positions of A and D. We get a 3 here in the first row, first column, and we have a 1 in the second row, second column. And then we negate the element first row, second column, and second row, first column. Now I usually just leave it like this, where you have 1 divided by some number. In this case, it would be 3 minus 8, which is negative 5. And this is my answer. And you can multiply it if you want to make sure. I want you to try one on the accompanying worksheet. Let A equal 3, 4, 1, 2. Find A inverse. The next topic I want to talk about is finding the inverse of an n by n matrix. Given a matrix A, to find A inverse, we augment A with I sub n and use Gauss-Jordan to put AI into reduced row echelon form, IA inverse. So we start by augmenting A with the identity matrix I, and then we use Gauss-Jordan elimination method to reduce this augmented matrix into reduced row echelon form, which will have an I on the left, and on the right will actually be A inverse. Let's go ahead and do an example. Find A inverse if A equals 4, 2, 3, 3, 3, 2, 1, 0, 1. All right, so again, first step, we augment A with I sub n, and in this case it will be I sub 3 because we have a 3 by 3 matrix A. So we need to augment with I sub 3. So we'll have 4, 2, 3, 3, 3, 2, 1, 0, 1, and we augment this matrix with the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, there is actually a reason why this process works, but it's very far beyond the scope of this class, and it'd be hard to prove without going well beyond the scope of this class. First step when we do reduced row echelon form is I want to get a 1 here at this location. In order to do that, we have 3 operations that we can perform. Add a constant multiple of one row to another row, multiply a row by a constant, or interchange 2 rows. Since we have a 1 in the first location here, I'm just going to interchange row 1 and row 3. So that I can get my matrix to have row 1, to have a 1 in the A11 location. 1, 0, 1, 0, 0, 1. We apply the operation to the entire row. Row 2 didn't change, 3, 3, 2, 0, 1, 0. And then row 1 moved to row 3. So 4, 2, 3, 1, 0, 0. This is our new augmented matrix. Next step I want to do is I want to get a 0 here. So I need to figure out what I can do in order to get a 0 here. Again, there's 3 things that we can do. Interchange 2 rows, multiply a row by a non-zero constant, and add a non-zero constant multiple of one row to another. In this case, we're going to have to do add a constant multiple of one row to another. So we're going to multiply row 1 by 3 and subtract row 2. 3 row 1 minus row 2, and we replace row 2 because I want to change this element. I'm also going to eliminate my 4 by getting a 0 here. Same idea. I'm going to multiply row 1 by 4 and then subtract row 3. 4 row 1 minus row 3, and we replace row 3 like this. Right? First row doesn't change. 1, 0, 1, 0, 0, 1. Now the second row is going to change, and we're using this manipulation here. 3 row 1 minus row 2. 3 times 1 is 3, 3 minus 3 is 0. We should have a 0 here because that's how we came up with this particular manipulation, was to get a 0 here. That's what we got. Okay, 3 times 0 minus 3. 3 times 0 is 0. 0 minus 3 is negative 3. 3 times 1 is 3. 3 minus 2 is 1. 3 times 0 is 0. 0 minus 0 is 0. 3 times 0 is 0. 0 minus 1 is negative 1. And 3 times 1 is 3. 3 minus 0 is 3. Now I want to get a 0 here in this row. So we do 4 times row 1 minus row 3. 4 times 1 is 4. 4 minus 4 is 0. And again, we got a 0 exactly where we wanted it. Again, because we wrote this out specifically to get a 0 here. 4 times 0 is 0. 0 minus 2 is negative 2. Next, 4 times 1 is 4. 4 minus 3 is 1. Then 4 times 0 is 0. 0 minus 1 is negative 1. 4 times 0 is 0. 0 minus 0 is 0. 4 times 1 is 4. 4 minus 0 is 4. And remember, in reduced row echelon form, we want to get zeros above and below each leading entry. And we want to have a leading entry of 1 for each of them. So the next thing to do is to get a 1 here. Now I don't want to use the first row to manipulate this one in any way, because then I'll lose the 0 here. And I don't want to lose that 0. I want to keep my 0 here, but I want to change this to become a 1 in some way. Now there's 3 options. Remember, we can interchange 2 rows. We can take a constant multiple of 1 row and add it to another row, or we can just multiply a row by a non-zero constant. There's 2 things really that we can do. Interchanging 2 rows is out of the question. So either we divide this row by negative 3, or we use some sort of manipulation in between these 2 rows to get a 1 here. That's actually what I'm going to do. I'm going to do row 3 minus row 2 replace row 2. Now, you might take an extra step if you want to, just to understand it a little bit better. But basically, I want to take my negative 2 and subtract a negative 3 so that I add 3 to it. Negative 2 minus a negative 3. The same thing as adding 3, which is 1. That's going to give me the 1 that I want. All right. Row 1 and row 3 are not changing. 1, 0, 1, 0, 0, 1. 0, negative 2, 1, negative 1, 0, 4. Row 3 minus row 2. 0 minus 0 is 0. Negative 2 minus negative 3 is a positive 1. And that's exactly what we wanted. That's how we got this. 1 minus 1 is 0. Negative 1 minus 0 is negative 1. 0 minus negative 1 is a positive 1. And 4 minus 3 is 1. Remember, we need to get to reduced row echelon form. So basically, we need the identity over here. We're almost there, but we're not quite. So I need to eliminate this negative 2 next. I need to make this negative 2 a 0. So I again am going to use my row 2 to manipulate row 3. So it'll be 2 times row 2, add to row 3, replace row 3. So if we multiply 1 by 2 and then add it to a negative 2, we get a 0, and that's what we want. So again, row 1 and row 2 have not changed. So we got 1, 0, 1, 0, 0, 1. Row 2 hasn't changed either. We get 0, 1, 0, negative 1, 1, 1. And 2 times row 2 plus row 3. So 2 times 0 plus 0. 0. And we want to keep that 0 there. That's why we don't use row 1. 2 times 1 plus negative 2. So 2 times 1 is 2. 2 plus negative 2 is 0. 2 times 0 is 0. Plus 1 is 1. 2 times -1 is -2. -2 plus a -1 is -3. 2 times 1 is 2. 2 plus 0 is 2. 2 times 1 is 2. 2 plus 4 is 6. This is what we have so far. We have one more step we need to do because we need to eliminate the 1 in the third column here. Third column, row 1. I need to get rid of this 1. I need to make it a 0. So we're going to use row 1 and row 3 to manipulate this 1. We do row 1 minus row 3. Notice that I did row 1 minus row 3 and not the other way around because I want to eliminate this. And I could either do 1 minus 1 or 1 minus 1 and get a 0 here. Either way. But if I look at the first column, I want to keep this entry positive. So I want 1 minus 0 and not 0 minus 1. Because 0 minus 1 is -1, I want a 1 minus 0 instead. Row 1 is changing, row 2 and 3 are not. 0, 1, 0, -1, 1, 1. And 0, 0, 1, -3, 2, 6. Now we do row 1 minus row 3. 1 minus 0. 1. 0 minus 0. 0. 1 minus 1. 0. 0 minus -3. The positive 3. 0 minus 2. -2. And 1 minus 6 is -5. And now I have it exactly how I want it. I have reduced row echelon form. Notice that I have the identity on the left side now. This is the identity. This will be A inverse. So my A inverse is 3, -2, -5, -1, 1, 1, -3, 2, 6. And that's how we do these types of problems. They take a long time, and you have to be very careful when you're doing the manipulations, when you're coming up with the manipulations, and when you're doing the actual math. Because if you make one mistake early, then your problem becomes compounded as you move through the problem. Try one on the accompanying worksheet. Find the inverse of A, where A is equal to 2, 4, 1, -1, 1, -1, and 1, 4, 0. You should be able to just follow the same process, obviously with different manipulations in between the steps. The next thing I want to talk about is the matrix equation. Recall, a system of equations can be written AX equals B, where A is the coefficient matrix, X is the column matrix of variables, and B is the column matrix of solutions. So if we write this out, AX equals B, and we want to solve this, supposing that A is invertible, then we can say, well, if we have A inverse and we multiply it to A, we're going to get the identity matrix. But that means we have to multiply A inverse on the right side of the equation also. Now, since we get the identity matrix here, we would end up with just I times X, which is just X. It's actually pretty easy to solve if we can find the inverse of A. Now, that's the problem, is generally finding the inverse of A is kind of tricky. Solving a matrix equation. If A is a square n by n matrix that has an inverse A inverse, and if X is the variable matrix where B is a known matrix, both with n rows and n columns, then the solution of the matrix equation AX equals B is given by X equals A inverse times B. Exactly what I showed before. If we have this matrix equation, if we left multiply the inverse, then A inverse A gives us I, the identity matrix. Now remember, the identity matrix doesn't change anything. When you multiply any matrix by an identity matrix, it does not change anything. But we would be left with A inverse B on the right. So we would just have X is equal to A inverse B. Let me show you this with a relatively straightforward matrix equation. Solve the system. 3x plus 4y is equal to 10. And 7x plus 9y is equal to 20. So this implies then, if we write this as a matrix equation, we would get the coefficient matrix A, 3, 4, 7, 9. The variable matrix XY is equal to the column matrix B, which is 10, 20. Here's our A, here's our X, here's our B. Now all I need to do to solve this matrix equation is multiply by A inverse on both sides. You have to left multiply. Right multiplying won't do anything because you have the X right here. So you need to left multiply. Remembering that matrix multiplication is not commutative. So first we need to find A inverse, and it's going to be 1 divided by 3 times 9 minus 7 times 4 times 9, negative 4, negative 7, 3. If you remember how to find the inverse of a 2 by 2 matrix, you flip these two entries and you negate these two entries. Then you multiply that matrix by 1 divided by AD minus BC. 3 times 9 is 27, minus 7 times 4, which is 28, gives us a negative 1. 9, negative 4, negative 7, 3. And if we just negate everything, we end up with negative 9, 4, 7, negative 3 as our inverse. So this is our inverse to the coefficient matrix A. Now all I'm going to do is left multiply A inverse to this matrix equation, both sides. We do negative 9, 4, 7, negative 3 times 3, 4, 7, 9. And we still have our 8x, our variable matrix. And remember, we left multiplied the A inverse on the left side of the equality, so we need to left multiply it on the right side also. Negative 9, 4, 7, negative 3. Times our B matrix, which is 10, 20. Now, these two multiplying together should give you I2 specifically, but I, the identity matrix. And we can make sure of that. Negative 9 times 3, negative 27, plus 4 times 7, which is 28. That gives us a 1. First row, second column. First row, second column. Negative 9 times 4, plus 4 times 9, that gives us 0. So first row, second column. Now second row, first column. Second row, first column. So 7 times 3 plus negative 3 times 7 is also 0. And then 7 times 4 is 28, plus negative 3 times 9, which is negative 27. 28 plus negative 27 is 1. And here we multiply. We do first row, first column, and second row, first column. Notice that we have a 2 by 2 matrix and a 2 by 1 matrix. So our final product Our final matrix is going to be a 2 by 1 matrix. First row, first column, and second row, first column. We do first row, first column. Negative 9 times 10 is negative 90, plus 4 times 20 is 80. So we have a negative 10 here. And then 7 times 10 is 70, plus negative 3 times 20, which is negative 60. So 70 plus a negative 60 is positive 10. Now notice, this 1 times this identity matrix times this matrix will be exactly this matrix. This should make sense because this is the identity matrix. When you multiply, when you use an operation on an identity, that identity doesn't change anything specific to that operation. For instance, adding 0 or multiplying by 1. Same idea with matrix multiplication by the identity matrix. So if we have an identity matrix under the matrix multiplication operation, it will not change this other matrix. And we can see that, again, we have a 2 by 2 matrix and a 2 by 1 matrix. So the result is going to be a 2 by 1 matrix. First row, first column is just X. Second row, first column is Y. Notice that it didn't change anything. That should be expected, because it's the identity matrix. So we end up with this. This means that X is equal to negative 10, Y is equal to 10. Try one on the accompanying worksheet. Use the inverse that you found in the previous try one problem to solve the system. 2x plus 4y plus z is equal to 10. Negative x plus y minus z equal to negative 3. And x plus 4y is equal to 6. All right, that's going to be it for today. I will see you all in the next lecture.